Again, welcome to Kruse Training. I hope you're doing well. This is Kruse, and I hope you have time today because we will go through a very important program today that is cause and effect behaviors in injection molding and shrinkage and warpage. That is so important. So let's get started with the overview. So what we're going to discuss today in the webinar is the cause and effect behaviors in injection molding. We will talk a little bit about a circle of knowledge training and then go through the process of understanding shrinkage and warpage. We'll go through that particular lesson today. And we have a little Q&A, so if you have a question, feel free to put it into the chat, and if we have enough time today, we'll get to it. But also remember, you are very welcome to send me an email if you have a very specific question that takes a little bit more time to answer. Please just send us an email. You will have my email in the invitation, or at the end of this presentation, I will show it to you again. Okay, so injection molding, we all are in injection molding business, and we do understand the complexity of injection molding. But understanding complex behaviors and interactions in the molding industry is really critical in order to stay competitive and ready for the future. That is definitely a very important because if you are in the injection molding business, you really need to know the part design, the mold design, the processing. Somebody said you can't hear me. If you can't, let's see.
No, can hear.
Can everybody hear me?
Yes.
Okay, thank you. Sorry.
Yes, I can hear.
Wonderful. I appreciate this, everybody. So let's continue. So complex behaviors are very critical to understand. So when we talk about injection molding, we have to talk about part design, mold design, and polymer material in the process. The combination of all of those together is really the key to understand injection molding. And I've often been asked to say, well, I'm just a processor. Why do I need to know part design, mold design, and material? Well, it's so important because if you don't understand the interactivity between all of these factions, you have a hard time really optimizing a molding process at the machine. So it is really critical that, in my belief, you really need to, know that. So let's continue. So every molded part has a certain criteria or molded part requirements, we call those. For some, you have critical dimensions and tolerances you have to meet. You have structural strength and requirements that are important. Of course, appearance and aesthetics, acceptable shrinkages and warpage behavior, and of course the assembly functionality. Those are all very important molded part requirements. We need to understand those requirements, okay? That's very important. If you understand these requirements, you can optimize a part design. And only if you can optimize a part design in the combination with the polymer material, then you should go into tooling. And then the processing obviously is a lot easier. You get a much wider process window if you follow some guidelines in that regard. Now, what we have here in Kruse training is a collection of knowledge, I would call it that way. For the last 30 years, I'm in injection molding. For the last 25 years, I'm performing simulations for the injection molding industry. And I found that when you run simulation, it's really a virtual tool into the molding behavior. So, and usually I work with part designers, mold designers, and processors, and trying to guide them along of, understanding this behavior so they can make the right decisions. And if you make the right decisions from the get-go and from part design standpoint forward, you have a lot easier time to mold a high-quality product. So if you have a chance, just check everything out on krusetraining.com. It's a very comprehensive program. We are adding 20 or 24 new lessons every year. It's almost like, think about it as a Wikipedia for injection molding. That's really my goal, is to put knowledge out there for everybody to access, to really help yourself in understanding injection molding business. Okay. So let's get started. Today's lesson is Understanding Shrinkage and Warpage. This will be a pretty long lesson. I would think it takes at least 20 minutes to do that. So stay with me. I will stop in between once in a while because there's some really interesting aspects I want to talk about during this lesson. So stay with me, okay? And let's get started. Here's our program. I have logged in, of course, and let's find the lesson for today. Let me see where it is in the lesson lineup. All of these lessons, as you can tell here, are available. No, right here. Okay, that's the one we want to discuss today, is Understanding Shrinkage and Warpage in Molded Parts. So let's get started.
Minimizing volumetric shrinkages and reducing part warpage are important considerations when designing injection molded parts. By understanding the interaction of part and mold designs, polymer material, and the molding process, preventative measures can be designed into the molding system to minimize shrinkage and warpage. In the first lesson of this section, we will take a detailed look at various factors that could lead to differential shrinkage and part warpage behaviors. In this lesson, you will learn the causes of shrinkage and warpage in injection molded parts, how part design variations affect volumetric shrinkages and resulting part warpage, how the following affect shrinkage and warpage behaviors: part design, mold design, cooling behavior, polymer material characteristics, processing steps.
As we all know and just discussed, injection molding is very complex, and shrinkage is one of those quality criteria in a part that is really difficult to ascertain what is exactly the cause for shrinkage and warpage, unless you really do an in-depth study. In general, you can think of it as everything plays a role to determine the final volumetric shrinkage, the final part dimensions. They all link to the part and mold design, to the cooling behavior inside the mold, the material, and of course at the processing. So right here you can tell shrinkage and warpage is really the ultimate test for a molded part to withstand, and being able to mold a part in tolerance. So this is really, really important, okay? All of these aspects.
Warpage in injection molding is the result of unequal volumetric shrinkage of material throughout a part as it cools and changes from a liquid to a solid state. Variation of temperature and pressure initiate the change of specific volume and polymer density, which can result in warpage of an injection molded part. Polymer materials naturally expand when they are heated and shrink as they cool. If polymer shrinkages are even in all directions, there is no resulting part warpage. Warpage only occurs when there are uneven shrinkages. There are various factors that could create uneven shrinkages in all stages of injection molding, from part design and mold design to polymer material to processing.
Okay, one more time. This is very, very interesting and important to understand. If you have even shrinkages in a part in all directions, you will have no warpage. You will only have a reduction in the size of the part. But if you have uneven shrinkages due to various factors like different wall thickness, different cooling rates, different shrinkages of the material inflow versus perpendicular to flow. So there are so many factors that create shrinkages. But the key here is that if you have even shrinkages, the part will not warp. So for us, it is important to identify what really causes this warpage.
There are a number of design considerations that impact shrinkage and warpage behaviors in molded parts. The overall design complexity of a part and wall thickness variations may cause uneven shrinkages and part warpage. Part design features such as ribs, gussets, flanges, bosses, chamfer, and radii all add varying levels of complexity to a molded part, and so can play a role in shrinkage and warpage behaviors. The type and number of features needs to be carefully considered to prevent potential molding issues.
Yeah, I mean, we design parts all the time. We look at parts all the time. We try to mold parts all the time. And, we know that ribs play a significant role in how a part is behaving, the stiffness, how it warps, how it shrinks, even bosses. Sometimes bosses have thick sections. Those thick sections can cause higher volumetric shrinkage, sink marks, voids, and even warpage. Yeah. So the part features and the overall wall thickness variation in the part is really key to optimize a part design in combination with the material to avoid designing warpage into the part. You're supposed to design it out, not in. Be careful.
Optimizing part design and polymer materials are the crucial first step in minimizing shrinkage and warpage. If the part design is not optimized for the material, the molded design cannot be optimized. Then, once the part reaches the processing phase, a process engineer has very little opportunity to optimize the molded part.
We all know that. We get molds into the machine and we'll never be able to mold a quality part because the part design has not been optimized. There's a thick wall somewhere and we always have sinks. We're trying to get rid of the sinks, but we can't. Yeah, and if we pack the part out too much, then we have molded in stress and the part will warp. So it is very crucial that processors at the machine really understand the part design to be able to give recommendations, say to the designers, part and mold designers, say, hey, we can't make this part because it is not optimized due to certain various factor in the part design. Everything starts with the part design. If the part design is not optimized, the mold cannot be optimized and the process will be challenging.
Next, let's look at mold design considerations that influence volumetric and linear shrinkages, and potentially part warpage. Mold designs must accommodate the optimized part design and allow for proper heat exchange between the molded part and the tool's cooling system. Remember, a mold is a heat exchanger, and the goal is to achieve uniform temperature distribution and removal, allowing for uniform polymer shrinkages. Important design criteria that affect this include gate location and size, runner design and size, mold cavity layout, ejection functionality, heat transfer between mold components, mold steel selection, and mold cooling circuit design, location, and sizing.
Yeah, I mean, we can tell that not only the part design is important, but all of the factors in the mold design too. If the runner sizes are not are too small, we can maybe not transfer the pressure in packing all that well, which causes higher shrinkages and warpage. The mold cavity layout means basically too many cavities into a smaller space. The mold maybe overheats in certain areas. Ejection functionality, if we overpack a part, we may have challenges to push it off the core. Heat transfer, very, very important. If some components in the mold are not touching each other very well or have gaps in between, well, there is no heat transfer. So the temperature is affected of the mold steel. Mold steel itself, is a beryllium copper stainless steel H13. They all have different thermal conductivities and therefore influence the overall heat balance in the tool. Yeah, of course, cooling circuits, as you know, are the most important ones. Yeah, if we don't have cooling in the tool, we get a heat trap, which will then cause overheating and all sorts of challenges. So not only the part design is important to optimize, but all of these factors when you design a mold, be very, very diligent in understanding which components are really important and for a smooth operation and to optimize this mold design. Very, very crucial. Okay.
Gate and runner layouts and sizes influence how molten material gets delivered to the cavity. They also impact shear rates and temperature of the polymer moving into the cavity. Gate location impacts temperature distribution inside the cavity. Very small gate sizes and high packing pressures are often not effective because once the gate freezes, the higher cavity pressures are neutralized, resulting in higher shrinkages. Gate and runner layouts and sizes also influence packing pressure gradients inside the cavity and overall volumetric shrinkage behavior.
These are just a few of the process conditions that will impact the temperature of the material inside the mold. Remember, a mold is a heat exchanger. The hot plastic is pushed into a cold mold, and a three-dimensional heat exchange will take place. In some areas, you may have an easier time to withdraw the heat from the plastic than in others. The wall thickness, of course, will play a role. So it is a huge can of worm that is very difficult to understand if you're not trained on cause and effect behavior from all of the components. The part design, mold design, and processing material all play a role in determining the processability of a mold and therefore shrinkage and warpage.
Cavity layout determines overall temperature distribution. A small or condensed cavity layout, combined with a greater part volume of injected material, would create localized heat concentration, while a wider cavity layout would distribute heat over a larger mold area. A small cavity layout with inadequate cooling could create a heat trap in extremely hot mold steel conditions. A wider layout would increase the runner length and volume, material consumption, and potentially require a bigger mold base and a bigger machine.
Again, very simple example. This is just an example to show that, certain areas in the tool, just think about this. All of these parts are densely packed into a tight cavity layout situation. If this cavity layout is not properly cooled, you get a heat trap. and you have a very great challenge on your hand to maintain the mold temperature here in this area if it's not properly cooled with an advanced cooling system. Of course, here, this layout is not ideal by any means. It's the same number of cavities. They're spread further apart. We waste a lot of material due to the longer runners, but the temperature behavior here is just really different. So what I'm trying to say here is, please understand how the cavities are laid out, understand where the heat is inside the mold, because the heat will drive the cooling of the material and therefore shrinkage and warpage, because that's really, really what we're talking about here, shrinkage and warpage. Create a heat map inside of your mold, A side, B side, measure the temperature of each cavity, map it down on a piece of paper to see how equal it is in the tool. Maybe you discover something.
Of course, part design complexity influences mold design complexity. The functionality of the mold determines the number of inserted components, slides, and the ejector system layout. As more inserted and moving components are added to a mold design, the greater the complexity. The number of these components can lower thermal heat transfer effectiveness, which makes it more challenging to maintain uniform heat distribution through the mold. A mold cooling system is important for optimizing heat balance, shrinkage behavior, and cycle time. Choosing the optimal mold steel for each molding application is an important factor to consider, since different steels have different thermal characterizations, which change how heat travels through the mold. Stainless steel has lower thermal conductivity than H13 and L7, for example. Beryllium copper alloys have high conductivity and can be used to reduce heat traps inside a mold. Cooling line layouts and sizes and circuit routings need to be optimized for proper heat removal. The condition of the water temperature, and consistent delivery of water flow also impact heat behavior inside a mold.
Yeah, here's another whole slew of challenges. Yeah, from the cavity layout of the cooling circuits to the routing. How many loops do we put on outside of the tool? Do we have too many loops? Is the water therefore the water circuit very long, and the pressures that come from the mold temperature controller is not high enough anymore to really get good water flow rate through the system, and therefore we have poor heat transfer. So there's a lot of things that need to be taken care of when you set up a molding machine and a mold for processing.
Polymer material plays an essential role in shrinkage and warpage behaviors. Molecular structure and weight are the most important factors. Other key considerations are whether the material is amorphous or semicrystalline, the length of the molecular chains, whether it is filled or unfilled, what type of filler or reinforcements are used, the percentage of filler or reinforcement, and what types of additives have been added to the base polymer.
And here we go again. We have another subject, which is now the polymer material, and we add another whole list of possible challenging factors that will influence shrinkage and warpage. Yeah, so again, this is very important for you. That's the reason why we are teaching the cause and effect behavior in injection molding. We want you to know the interactive behavior between part design, material, mold design, and the process, because they all influence each other. And if you understand this very complex behavior, you can be an extremely good processor or part designer or mold designer.
Molecular chain structure influences flow to warpage behavior. Remember, amorphous materials have random molecular structures, and semicrystalline materials have areas of dense and aligned crystalline structures. A molecular chain structure and length determines how it stretches during filling and then aligns inside the mold. Molecular alignment is also impacted by the overall process. For example, a material with a long branched molecular structure that is injected quickly into a cold mold will have a high degree of molecular alignment. Because they are frozen in alignment, the molecular chains do not have the opportunity to relax and return to their natural structure. This frozen in alignment will create flow-induced stress.
Yeah, again, this is back to the processing. Some materials have very long molecular chains, and I said, well, I don't care about that too much. Well, yeah, you shouldn't, but you have to, because long plastic materials with long molecular chains, they have a high degree of orientation. What it means is, in the direction of the molecules, you have a different shrinkage behavior than perpendicular to it. And now just add to the complexity, the part is a 3D dimensional piece. We are not molding plaques. We are molding very complex designs. So the molecular orientation, the 3D design of a part is very, very complex. Then on top of it, the fill speed, for example, will influence the orientation of the molecules. Then the temperature of the tool versus the plastic will influence the frozen layer. So how much orientation we will freeze in. This frozen in orientation will determine residual stresses, which will result in, guess what? Yes, shrinkage and warpage.
Next, we will review how some aspects of the molding process can impact shrinkage and warpage behavior. Generally, polymer materials have a process range for melt and mold temperatures. In addition to these guidelines, other process conditions, such as fill speed, packing pressure and time, and cooling time, can influence overall molding behavior and therefore shrinkages and warpages. Looking at these factors in more detail, fill speed influences rheology behavior, shear heating, and molecular orientation during cavity filling. The fill speed should be as fast as possible to achieve uniform temperature distribution inside the cavity. But filling too fast can create shear heating, which could lead to material degradation. On the other hand, filling too slowly can cause frozen-in molecular or fiber orientation and uneven temperature distribution. Important factors that influence shrinkages are melt temperature, packing pressure, and time. Low melt temperatures reduce melt expansion, which results in lower overall shrinkages during packing and cooling. Less melt expansion during heating will always result in less shrinkage inside the mold. When packing pressure is high, the material compression is high, so shrinkages will be lower. These two factors taken together show that achieving lower overall shrinkages can be achieved with lower melt temperatures and higher pressures.
Yeah, these are just two of an array of process conditions that we have influence over. But just think about the melt temperature itself. So what we do is we heat the material, and when a material is heated inside the barrel, what happens to the molecules is they move apart further. So the material basically grows, it expands. So when you inject this material into a mold, it cools down and it shrinks. That's why plastics shrink, because they expand when they're heated and contract when they get cold. Now, if you start with a lower temperature on the melt, you have less expansion of the melt to begin with, therefore lower shrinkages overall. Yeah, lower temperature, lower shrinkage, because we don't expand the material as much. And the packing pressure, of course, is for compressing. Compressing the material, as higher the pressure, as more molecules we push into the same cavity, or that will occupy the same space. So as more we compress, as lower the shrinkage will be as well. Okay.
In this lesson, we will evaluate 4 different design shapes and analyze part shrinkage behavior that leads to warpage. The first analysis is a simple U-shaped part with a fan gate. The part is 300 millimeters long by 60 millimeters wide and has 5 millimeter wall thickness at the base and 2.5 millimeter thick upright walls. The part is molded in a POM material with a mid-range melt and mold temperature. The fill time is set for 3 seconds. Here you can see the filling behavior for the first part. Notice that the part fills from one end and not the walls. There is a slight lag in filling the upright walls because of the different wall thickness between them and the base. Looking at the maximum volumetric shrinkages of this part, you can see a high shrinkage of about 16% at the base due to the thickness. The upright walls show shrinkages from a low of 2.5% to a high of 10% at the intersection to the base. This example shows a wide range of volumetric shrinkages.
Yeah, I mean, again, this is just a very simple example. That's why we used it. We like to use simple examples in the beginning of our training, because if you understand the simple examples, you can transfer that information to complex part designs. But it's very key. The wall thickness here is really thick. It's 5 millimeter. Whoa, that's almost 200 thousandths of an inch. Yeah, and we have 100 thousandths of an inch for the side walls. So they are much thinner. And logically, the base has a lot more shrinkage. So 16% on a volumetric basis, that's a lot of shrinkage. And then you can tell on the sidewall, when you get a little further up, you go from 10 to 2.5. So there's huge shrinkage differences because of the wall thickness variation. Now let's see what happens to the part.
Looking at the resulting warpage animation, you can see that the part bends significantly. The central portion moves up by 6.4 millimeters, and the ends move in the opposite direction by 11.5 millimeters. This is a dramatic example of part warpage, resulting from uneven volumetric shrinkages. Let's look at how to reduce this warpage behavior by redesigning the part.
Yeah, I mean, this is really significant warpage. But again, we use this as an example to really show, oh my God, this is not what we should be designing. Yeah, just a simple example showing significant warpage bending of a part.
The part for the second evaluation has the addition of cutouts, which break up the geometry. The addition of the cutout to the design did not create any adverse filling results. The part fills without any issues, but the upright walls still show some lag in filling. The maximum volumetric shrinkage results on screen indicate high shrinkages, similar to the previous example. Let's see if the cutouts influence part warpage behavior. The animation shows that the cutouts did not have a significant impact on part warpage. The part still bends up in the center by 6 millimeters and down 11 millimeters at the ends.
Oh, that's not good, yeah? So we changed the part design. What we really wanted to do is, if we put a cutout in here, we reduce hopefully we reduce the shrinkage in that wall, and therefore give the part the opportunity to shrink more equally and have less warpage. But no, that really did not work. Again, a very simple change to a part design in this case didn't make any difference.
The third iteration of this design has the same cutouts as the previous example, but now they extend down from the base of the part.
That is significant. Look at this. The cutout is all the way to the base, not the one before was we had a cutout, but it was not all the way to the base wall thickness.
The filling animation shows that the part fills without any issues. The maximum volumetric shrinkage results still indicate the same uneven behavior as the two previous examples. The shrinkages in the base wall are 16%, and in the side wall they range from 2.4% to 10% at the intersection to the base.
Now, what would you think? Do we see a difference in the shrinkage, in the warpage, I'm sorry? Just remember, we had a part with a full wall thickness all the way through, a wall all the way through. Then we had some cutouts, but they didn't go all the way down to the base. Here we went all the way down to the base.
The warpage behavior for the third design shows a significant difference in warpage behavior. The warpage range is now from 1 millimeter in the center to about 1.3 millimeters at the ends. Why does this design show so much improvement? The cutouts that reach the base allow the base to shrink freely lengthwise because the part is no longer constrained by the upright rib connection to the base. The previous example proved that even a small upright wall can obstruct the base from shrinking freely, which resulted in the part warping. Remember, shrinkage is a normal behavior. If shrinkage occurs evenly or unobstructed, then there is no resulting warpage.
Yeah, so one more time. We cut it out all the way to the bottom. Now this base can shrink freely in the length direction. There's no obstruction anymore. This dimension between the cutouts gets smaller. And therefore, the part shrinks more evenly. Small design changes can have a huge impact on how a part shrinks and warps.
The final design example is the same part without cutouts, but with two upright walls, like an I-beam. The filling animation for this part does not indicate any issues, aside from a slight lag filling the upright walls. The maximum volumetric shrinkages, again, have not changed, and you can see there is still high shrinkage at the base of about 16%. The final animation for the I-beam design has similar warpage behavior to the previous design, with the cutouts that extended to the base. The center portion is warping down by about 0.7 millimeters, and the ends are up about 1 millimeter.
Yeah, so we have another design that is pretty even. For a large part like this, it's pretty even. So what it basically did is, before we had just a U shape, now we have an I-beam. So we have the shrinkage that happened to bend the part. Now we have two walls that are equal on either side, which will basically stabilize the warpage in the part. An I-beam has a better shrinkage behavior than just a U-shaped part in this particular case. Again, a simple example of how a part design can impact shrink and warp.
On screen, you can see the warpage results of the 4 designs. Clearly, the warpage behavior changes significantly based on the design. The volumetric shrinkage range differences in the base and upright walls are so large that the part warps. The design components must be allowed to shrink freely. So by creating cutouts that extend to the base or changing the upright wall design, the warpage was minimized. This proves that design matters. This concludes Processing, Shrinkage and Warpage, Lesson 1, Understanding Shrinkage and Warpage. In this lesson, you learned the causes of shrinkage and warpage in injection molded parts, how part design variations affect volumetric shrinkages and resulting part warpage, how the following affect shrinkage and warpage behaviors: part design, mold design, cooling behavior, polymer material characteristics, processing steps. By learning the fundamentals of how changes to simple geometries can impact shrinkage and warpage behaviors, you can expand that understanding to more complex part designs. Designing and building robust molded parts is dependent on understanding the interactions between part and mold designs, polymer material, and the molding process, and their impact on shrinkage and warpage behavior.
Well, everybody, that was a quick review of a very, very simple part design that causes shrink and warp challenges. So as we've seen, there are many factors in injection molding that are responsible for the shrinkage behavior of a molded part. From the polymer, the part design, the mold design, the processing, the machine, everything has an impact on the shrinkage behavior of a molded part. So it is important for us to really mention this and put it to your heart. Learn injection molding from all aspects, not just processing or not just part design or not just mold design. Try to understand the interactive behavior in injection molding, because this really will make a big difference in how you view the injection molding industry. So again, thank you for participating. If you have any questions, don't hesitate. You have my internet access, Kruse Analysis, krusetraining.com. Send me an email, please. Don't hesitate. I'm here to help. I'm looking forward to hearing from you. And other than that, stay healthy. We'll talk soon. Next year in January, we have another webinar set up. I hope you can manage to come and be part of this again. So again, thank you for participating and have a wonderful day.